Okay, so I think we're ready. We're ready to start. So thank you all to come here. Okay, so today we're very happy to have with us Akash Dixit. And Akash Dixit was until 2 years ago or last year, graduate student at Chicago, and he did some great work on the use of qubits to detect single photons in resonant cavities through these non-demolition measurements, which is of really great significance for the world advancing axion detection. So we're very happy that he's here. He will spend the whole week with us. Next week we'll actually be in Canfranc, and so we're interacting with him a lot for the Radis collaboration, but anyone is welcome to talk to him also these days. So thanks very much, Akash, for please go ahead.
Thanks, Jordi. Thank you all for being here. Thanks for putting this together and bringing me all the way from Colorado to Barcelona. So I appreciate that. So today I'll tell you about some of the work, like Jordi mentioned, that I did in Chicago with out of the way. So yes, I'll tell you about some of the work I did at the University of Chicago with my advisors, Aaron Chu and David Schuster, and a bunch of great graduate students and postdocs as well. So title of the talk, Searching for Dark Matter with Superconducting Qubits. I probably won't spend too much time talking about the dark matter aspect of this, a little bit of details here and there. And hopefully I'll give you an introduction about superconducting qubits and how these two topics, though they may seem very different from each other, kind of go together. Okay, so first, what is dark matter? Everybody has to have this slide, right? Why do we even think there is dark matter? There's sort of lots of lines of evidence that point towards this idea of dark matter. Of course, some being looking at radial velocities of stars inside of galaxies and being anomalous and consistent with living inside a halo of matter. If you look at the spectrum of the CMB, it's consistent with this additional matter. And I think probably the most compelling evidence to me is the structure of the universe that we see. It indicates that early on we had to have large amounts of mass to gravitationally bind matter together, which results in galaxies, structures, planets, and us. And so these kind of all come together to lead us towards the idea of dark matter. But of course, as an experimentalist, I want to ask, well, what is it? And there are many hypotheses for what dark matter is. When I was an undergrad, I worked on something called weakly interacting massive particles, and they all have interesting, funny names sometimes. But today in this talk, we'll focus on a specific class of dark matter hypotheses, namely the ultralight dark matter hypotheses. And I'll sort of zoom in a little bit more into the class of hypotheses, and I'll mention two of them. The first is the axion dark matter hypothesis, and the second is called a hidden photon. And as an experimentalist, again, I like to ask, okay, well, maybe we have a hypothesis for what dark matter is, but how can we detect it? And so one way we like to think about this is how might the dark matter couple to, say, electromagnetism, so then we can sense the presence of this dark matter. And so part of the hypotheses for, say, the axion and hidden photon are that under the right conditions, they could convert into a photon. And the frequency of the photon is related to the potential mass of the dark matter. And these typically come out in the microwave regime, so a few gigahertz photons. And so here's some references about the people who've thought about these hypotheses and how they arise from part of the early cosmology of the universe. Okay. So now that we have these hypotheses for dark matter and how they might couple to electromagnetism, I won't get into the details of that. My job as an experimentalist is, how do I see a microwave photon? And so let me walk you through quickly the typical detection mechanism for one of these experiments. So first, you build a resonant microwave cavity. So this is a cavity whose size is matched such that it resonates at the frequencies of the photons that you're interested in looking for. And then what you do is you poke a hole in that cavity, you put an antenna in there so you can see the antenna right here. And then you draw that signal out to some sort of nice amplifier. In recent work, people have started using these quantum limited amplifiers, using these new technologies, quantum technologies. And then you amplify the signal and you digitize it and you measure it. And so what you're looking for is the rare occurrence of a signal inside of the cavity when there nominally should be nothing if you don't put anything in there. And that you attribute possibly to the dark matter coming in and depositing a photon. Okay. Well, there are a couple of drawbacks to this type of detection mechanism, mainly the two that I'll mention here in this talk. A priori, you don't know what mass the dark matter is, so you don't know what photon frequency you should be searching for. And what that means is you basically have to tune the cavity, just like you tune the knob on your radio in your car. You have to tune the cavity frequency to check different potential dark matter masses or photon frequencies. Unfortunately, as part of this tuning, as you go to higher and higher frequencies, you get some poor scaling for the noise as well as the signal that you're potentially looking for. The noise, in fact, using one of these quantum limited amplifiers, just stays flat as you change the frequencies. The signal, however, decreases, and this really comes from the fact that as you increase the frequency of your cavity, the size of the cavity has to shrink in order to maintain that resonant condition. This is just the relationship between the wavelength and the frequency here. And as you shrink the cavity, the volume decreases, and so the signal decreases proportionally with volume. And so you get these poor scaling for both of these types of things. So we've had to start thinking about, well, what are some ways in which we can try to overcome these potential limits? And that's sort of where I picked up my research. And so in this talk, I'll tell you about two strategies we've thought about for overcoming these poor scaling that we have for the dark matter searches. The first is, well, don't use the typical amplification technique that people have been using, but instead circumvent the quantum limit of that amplifier by doing something like counting photons. And I'll tell you why that works and how we do it exactly. And the second thing that we've recently started working on is, though your signal is diminishing as you go to higher and higher frequencies, maybe there are ways in which you can use quantum techniques to enhance the signal. And here we do something called stimulated emission to do that. So I'll probably spend most of the talk talking about the first thing, since that's what I worked on most, and then I'll spend a few slides, a few minutes at the end talking about the second topic as well. Okay, so just to describe the typical technique of amplification. So what are you doing when you amplify? Basically, you're looking at both the in-phase and out-of-phase quadratures of the field that's coming out of the cavity. And the in-phase and out-of-phase quadratures obey a Heisenberg uncertainty relation, just like position and momentum. And so you can't measure both components of this field with arbitrary accuracy because you have this uncertainty relation between them. And that leads to an effective photon number equivalent of 1 photon's worth of noise from the fact that you can't measure both at the same time. And that's sort of what is really just a manifestation of Heisenberg uncertainty principle for measuring fields in and out of phase quadratures of fields. And this is what people mean when they say quantum limited amplification, that you're working where at the regime where Heisenberg uncertainty principle is your limiting noise and not the noise or the loss inside of your amplifier. So developing these is already a challenge, but there is a limit to how well they can perform. And it's essentially this 1 photon's worth of noise. So what we thought about was, how about we don't measure both quadratures of the field, instead just measure the amplitude of the field. And again, the amplitude is part of an uncertainty relationship, just not it's part of an uncertainty relationship with the phase of the field. So by measuring the amplitude of the field, we give up complete information about the phase of the field. So where exactly did the signal start, essentially? But for the purposes of doing a dark matter search, this is completely fine for us. All we want to know is, did the dark matter deposit a photon or not? And by measuring the amplitude, we can answer this question. And so this is sort of the trick that we've been thinking about. We don't, of course, break this Heisenberg uncertainty principle. We just sort of circumvent it by putting all of the uncertainty in the phase and having accuracy on the amplitude only. And this is what I mean by counting photons. And I'll tell you exactly how we do that. see here. Okay, so people have probably already thought about counting photons. People do this at high frequencies with photomultiplier tubes or superconducting nanowires. These typically, however, are detectors for very high energy photons. These are very high energy processes that you can use these type of detectors for detecting. However, the types of photons we are looking for are microwave photons. They're very low energy, and these type of detectors don't work well to detect these types of photons. So we have to develop something slightly different. And that's sort of where the next part of this topic comes in. The way we go about detecting low energy microwave photons is by using superconducting qubits. So take a little water break here. So the typical device that we operate here looks something like this. So we have a microwave cavity that we call the storage cavity. We have another microwave cavity that we call the readout cavity, and there's a qubit that lives in between them. And the goal of this is we hypothesize that the dark matter deposits a photon into the storage cavity, and then we use the qubits to measure the presence of that photon. And the Hamiltonian that describes the interaction between a qubit and a cavity is written up here, and I'm going to go through each one of those parts in the next few slides. And for reference here, some of the frequencies associated with each of these qubits here. Okay, so microwave cavity. This is almost exactly like the microwave that we have at home. It's just a box that's used to contain light. However, the boxes we make are out of shiny, high purity metal rather than plastic and Teflon. And so in this case, we make them with high purity aluminum. And the Hamiltonian term that describes this is just that of a harmonic oscillator here. We did some interesting work where we designed a method for building seamless cavities. And you can see the method here where we drill a block from both sides so that there's an internal cavity in here whose size is much bigger than any of the individual holes. So we're able to contain photons in here without having any seams. So this is interesting work, useful for people in quantum information, but I just think it's generally a cool way to make a cavity. And there's a reference here as well. Okay, so maybe the most important part of this system is the qubit. So again, like I said, we're really good at building harmonic oscillators. LC circuits, everybody's great at doing that. How do you actually make a qubit? Well, we just start with an LC oscillator. And what we do is instead of using a regular inductor here, we use what's called a Josephson junction. And this adds a small nonlinearity such that now your LC oscillator is slightly nonlinear. And so maybe we can just quickly look at some of these pictures. This is a typical size scale of a qubit, sort of on the millimeter scale. And if you zoom in a little further, you can see this is sort of at the tens of micron scale. If you zoom in all the way to the Josephson junction, you can see it's over there. And the Josephson junction is really just like a sandwich of superconducting material, in this case, aluminum, and then a dielectric, a relatively lossless dielectric aluminum oxide, and then another superconducting material, in this case, aluminum. And you can see the first layer here, second layer here, and they're bridged by a gap of insulating aluminum oxide. And the size scales are sort of on the few hundred nanometers here. Okay, and the key here is once you build one of these nonlinear and harmonic oscillators, the energy levels of the system are no longer equally spaced like they would be in a linear harmonic oscillator. And what that means is the transition energy between the first and second state is not the same as the transition energy between the second and third state. And so you can sort of focus in on the subspace of energy levels and just operate between these two levels we can call the ground and excited state. And in terms of the representation, we sometimes just use a spin operator, just describing up and down, ground and excited. Okay. So I think the next important component of this is you have a cavity, you have a qubit. How do you put them together? And the way I like to think about it is really your qubit is just a dipole moment. And what you do is you couple that dipole moment to the electric field of the cavity. One of the really nice things about these types of systems is you can see here in the previous pictures, these are qubits that I fabricated and I designed. They're very customizable. You can choose the energy transition level that you want. You can choose the dipole moment that you want. So they're similar to like atoms in nature, except very customizable, right? And so you're building your own your blocks here. And then when you couple them together, you can get arbitrary couplings and you can engineer them to be what you want. I think that customizability is extremely useful for both quantum information sciences, but also for the things that we're talking about here in terms of dark matter. Okay, so going back to this, you have the dipole moment of the qubit coupled to the electric field of the mode inside of the cavity. There's some math that I do, but essentially you get a term in the Hamiltonian that looks like this, where you have an energy scale 2 chi. Again, an energy scale that you can completely engineer just by your design and your fabrication. And the terms in the Hamiltonian look like A dagger A and sigma z, which are again just the number operators of the cavity and the qubit. And there's some details about what that chi exactly is. And so maybe we can talk about that later for the people who are interested in exactly those things. Okay, so now I have a qubit, I have a cavity, they're coupled together. If I just hand you that, it really wouldn't do much. You have to go to very, very cryogenic temperatures, very cold temperatures, mostly for 2 reasons. One is everything is made of superconducting aluminum, so you need to get below the critical temperature of aluminum of about 1 Kelvin. And most importantly, I think, remember, we're looking for very, very rare incidences of a photon being deposited from the dark matter. And so we want to reduce the probability that there are any thermal photons in our system. So we need to reduce the temperature of all of these components to extremely cold, in our case, something like 10 millikelvin, in order to sort of mitigate the presence of thermal photons here. And this is typically what a fridge looks like. You can see this is the magnetic shield and the qubit and cavity are inside of that, and they're hanging off of a 10 millikelvin stage there. Okay. All right. So we have our qubit, we have our cavity, they're inside of a fridge, they're cold. How does this lead to photon counting? That's the real key. Okay, so again on the top, I've shown the same exact Hamiltonian. I've just grouped the interaction term cleverly with the qubit term. And now you can see everything before the sigma z tells you what the qubit frequency is. So it has its original frequency, but now it has a term that's related to the 2 chi interaction energy, as well as A dagger A, the number of photons that are inside of the cavity. So what this means for us is that the frequency of the qubit is a function of the number of photons inside of the cavity. And you can see that here in the data here, where each peak here represents a potential qubit transition frequency, and they're separated exactly by 2 chi, depending on if there's 0, 1, or 2 photons inside of the cavity. And so now the problem becomes, use your knowledge of the qubit's frequency to infer the number of photons in the cavity. And we can do this in a couple of ways. The way we do it is using interferometry. And so I'll show you the exact sequence we use there. So remember, we're really good at measuring frequencies. Counting photons is a little tough, but we've mapped those 2 things onto each other. So measuring the frequency of the qubit is equivalent to inferring the number of photons in the cavity. So how do we actually do that process? It's relatively simple, and like I was telling Jordy today, this is very reminiscent of a spin inside of a magnetic field. So if you have a spin aligned with a magnetic field, nothing really happens. But if you put the spin off axis, it precesses around essentially. And that's exactly the process we use here. So let's look at 2 cases, one where there are 0 photons in the cavity and one where there's 1 photon in the cavity. And this representation is of the qubit state. So if this vector is pointing down, that's the qubit in the ground state. If the vector is pointing up, that's the qubit in the excited state. And anywhere else on this sphere is some superposition of 2 for the qubit. So first what we do is we inject the pulse to put the qubit into a superposition state. And now, when there are 0 photons, the qubit frequency doesn't change at all, remember? But when there's 1 photon, the qubit frequency is shifted by exactly 2 chi here, this shift. And that shift effectively looks like turning on a magnetic field that's pointing in the z direction. And so in this case, now your qubit spin and your magnetic field are misaligned, and that spin starts to precess around the block sphere. Of course, in the case where there are no photons, nothing happens. There is no effective magnetic field. So if you wait the exact right amount of time for the case where there's one photon, you can get the qubit to go all the way around the block sphere to the other side. And then finally, we apply a pulse to bring them back onto the z-axis here. And you can see the net effect here. If there are no photons, the state of the qubit remains unchanged due to this process. But if there's one photon, the state of the qubit flips. So in this case, it goes from pointing down to pointing up. And so this is the effect we're looking for, right?
Can you explain one more time
Sure.
why it doesn't change with why there's no effective magnetic field in the case of 0 photons?
Yeah, it's because the qubit frequency doesn't shift if there are no photons, right? A shift in the frequency looks like turning on an interaction. In the case of a spin in a magnet, it looks like turning on the magnet.
So you always assume interaction with dark photon.
Sorry, say that one more time.
You always assume interaction of electromagnetic with some dark photon. Because the Hamiltonian seems to be no.
This is just qubit and cavity so far. The way the dark matter comes into this is that it could potentially populate the cavity.
So I mean, in the case of axion, for instance,
Yeah.
do you have direct interaction of axion with electromagnetic field? The usual one, you don't have.
Potentially.
So, I mean, yeah, if I understand correctly, you consider some channel from axion to dark photon, then from dark photon to.
No. Sorry. I was mentioning two separate hypotheses. One is the axion and one is the dark photon. And both of them have separate mechanisms by which they could potentially convert to a magnetic photon.
The dark photon can directly couple to electromagnetic, right?
Potentially, yes.
Potentially.
That's the idea, yeah.
So
And
an axion.
you have to add a magnetic field in order to do it, but if you set up the appropriate conditions in the lab, you can get it to convert to a magnetic photon. That's the hypothesis. Yeah.
Wait, so one more question.
Sure.
So when you have this, you create the superposition state, does the superposition state, like where it's not pointing down, does that not time evolve under the normal Hamiltonian?
It does, I've just rotated into that frame.
Okay.
Yeah, so they're both rotating at the qubit frequency.
But this is rotating slightly faster.
Exactly by 2 pi, exactly.
And so if you just wait long enough, then the difference in that frequency will
Builds up to this.
phase shift.
Exactly.
Measure, okay.
Absolutely. Yeah, I've moved into the interaction.
Okay.
For simplicity, I don't want to have videos where everything's spinning around all crazy. Yes, okay. So I'll just mention this again. No photon, nothing happens to the qubit. One photon, the qubit flips. That's effectively the interaction we've built here. Okay. So then we were like, okay, great. We did this. We made it work. Let's just go and try it. So here I'm showing sort of 2 cases. One where I start the cavity with no photons. One where I start the cavity with 1 photon, and then I just apply this measurement. Maybe I forgot to mention it, but we call this a parity measurement. It's not really that important right now, but for the experts in the room, that means not only am I sensitive to 0 or 1 photons, but I'm actually sensitive to even numbers of photons or odd numbers of photons. In the case when you have potentially very small chance of 1 photons, you can zoom in and just look at 0 and 1 photons. Okay, so in this case, we try the parity measurement a bunch of different times for different instances of putting 0 or 1 photons in the cavity. And you can see, okay, mostly I measure 0 when I think there's 0, and mostly I measure the 1 when there's 1. But sometimes you see these blips. So in the case on the right, you're basically seeing false negatives. You count that there are 0 photons, even though you actually put 1 photon in the cavity. And this looks like a false negative. And on the left side here, even though there were 0 photons in the cavity, you accidentally think that there's 1 photon in the cavity. And this is a false positive. And there's sort of asymmetric penalties for the false positives and the false negatives. For the false negatives, that's effectively like there was dark matter, but I missed it. Okay, maybe not the end of the world. I just tried again. For a false positive, there was no dark matter, but I accidentally said there was. That's a big deal. You should not be doing that, right? You should not be making claims like that. And so this is a serious problem. You can see that the false positives and the false negative happen sort of a few percent of the time, maybe 5 to 10% of the time. And that's a big deal. And it's a large number compared to how often we hypothesize that dark matter should actually deposit a photon into the cavity. And so we have to figure out a way to solve this.
How do you prepare these test cases? Like,
It's a little bit involved, but because there's a qubit in the system, we have ways of generating 0 and 1 photons in this storage cavity. It's a little bit involved, but I can go into it later. Okay, so again, it always comes back to the same Hamiltonian. And something I mentioned before but sort of glossed over was, if you look at the interaction term there, A dagger A sigma Z, it's just a product of the original Hamiltonian, the uncoupled Hamiltonian, A dagger A and sigma Z. And so what this means, this is something I learned in like first year graduate quantum mechanics, which blew my mind, was that if the interaction term commutes with the rest of the Hamiltonian, they all share the same eigenstates. And what this effectively means for an experimentist like me is, if I use that interaction to measure the state of the cavity, I just project it back onto one of its eigenstates. And with people call this a fancy name, this is called a quantum non-demolition measurement. I don't absorb the photon in the process of measuring it. I just project it back onto being the photon every time I make this measurement. And what this allows me to do is do a very classical thing, is just measure the same photon again and again and again to beat down the errors in each of the measurements. And that's exactly the sequence we set up here, where either I or the dark matter put something in the cavity, and then I repeat this parity measurement where I put the qubit in the superposition, let it rotate, and then flip it back. And then of course I need to read out the state of the qubit. And I just repeat this n number of times. Okay.
Was the plot you showed earlier on the previous page, was that
Just one.
what was that measure, were these sequential measurements?
No, it was just a single parity measurement of the state of the cavity.
Okay.
But that doesn't work because each time I make a parity measurement, I error a few percent of the time. But instead of just doing one, just make n measurements of the same photon. And I'm not measuring n different photons, I'm measuring one photon n times.
But the previous plot.
Yeah, this is a bit confusing, but yeah.
You have basically, whenever you make an error, you always go to 1. So the error is not bringing you typically 0.5, right?
Yes.
And the reason for that is what exactly?
Well, again, in quantum mechanics, remember, you can only measure your eigenstates. You either measure G or you measure E. So you measure 0 photons or you measure 1.
But your points show dispersion, right? So when you're 0, then there is a dispersion.
Yeah.
Close to 1 also. So what's that?
Oh, that's just my ability to read out the qubit is not 100%. I make some errors sometimes. So these are actually probabilities.
Okay, and so even when you're wrong, so you have no photon, but you get 1, then there is a reason that you get 1 there.
Yeah. That's right. So say for this instance here,
Yes.
maybe my qubit accidentally flipped, even though there were no photons, but I made a not so great measurement of it in the excited state.
Okay. So you are seeing the quantum nature of the qubit states, but sometimes the qubit state tells you the wrong thing about the photon.
Exactly.
Yes.
Exactly. So there are a few different effects all convolved together to give you this. And to answer your question, each of these is a single instance of an experiment. I do this, and then I just wait, and then I start the whole experiment over again.
So you reintroduce those 0 photons.
Or the 1 photon, exactly. But what I'm suggesting now is when I either put 0 or 1 photons, then do multiple measurements before I start the measurement. And that's sort of this sequence here. Okay, so once you sort of design a complicated measurement sequence like this, to sort of mitigate the errors that we think are occurring, what we do is then we build a model to capture all of these errors. And then once you have the result of this repeated measurement sequence, how do you then go back and determine whether or not there was a photon? And so we use something called the hidden Markov model, just a fancy model, but basically we include all the possible error channels, say like the qubit decays or excites accidentally, the cavity decays or excites accidentally, potentially dephasing of the qubit. So even when I put it in the superposition, if it jitters a little bit, those types of errors are included in here, as well as errors related to my ability to measure the state of the qubit once I either put it in the ground or excited state. And there's some math associated with this, and so we can go through that really quickly. But basically, we account for all of the errors. We build this model, and then once we have a sequence of measurements with our n parity measurements, we can use some formula to go back and then decide whether there were 0 photons initially or 1 photon initially in the cavity. And okay, that formula is opaque. It's very difficult to understand just by looking at it, but maybe let's take an example. Say if you observe a sequence where you read out that the qubit's in the ground state, and then you read out the qubits in the excited state. There are lots of terms that go into that equation, but these are sort of a breakdown of a few of them. One way in which you could get that particular sequence is there was a photon in the cavity, your qubit correctly flipped because there was a photon in the cavity, and then you correctly read out that the qubit has flipped. Great, that's perfect. Another way you could get this is there was no photon in the cavity, but the qubit spuriously flipped. It shouldn't have flipped, but it flipped. Happens a few percent of the time. And then you correctly measure that it's flipped. Alternatively, there could be no photon in the cavity. The qubit doesn't change at all, as it's supposed to, but you make a mismeasurement of the qubit state. And that again looks like it's flipped. And so these two are errors. This is the right behavior that we want. But we take all of these into account, and that this formula takes care of those things. And you can now go and ask, with a sequence of measurements that I have, what is the probability that, in fact, there was a photon in the cavity when I first started this sequence of measurements?
Are any of the errors correlated between sequential measurement?
This is a good question. We don't think so, right? Because we sort of reset the qubit each time. So these are all errors of the qubit or the readout of the qubit. So there's no reason we think that they should be correlated. People have started to do interesting work recently where very rare instances of a cosmic ray comes in, hits your qubit, and that can generate correlated errors across a big chip of, like, say, in Google or IBM or something like that. But those are spatial correlations, right? And we're looking for here temporal correlations, which we don't think that there's any reason to happen. And this model seems to capture the behavior pretty well, so we don't seem to suspect that that's a problem. It's a good question. Okay, so let's take a couple of examples. Here's some data on the left where I make repeated parity measurements and I track the qubit state in each of these measurements. So in most of these measurements, the qubit with very high probability remains in the ground state. Great. And then I apply this hidden Markov model analysis. I do all the reconstruction. It's like 4 lines of Python code. It's really not, it sounds much more fancy than it really is. But with very high probability, I infer that there are 0 photons after I take into account all 30 measurements. And I reduce the possibility that it was actually 1 photon that caused this event. This is the intended behavior, right? No change in the qubit state as I do these measurements. With very high probability, I decide that there was 0 photons in the cavity. Not that interesting.
But can you explain what's the difference between these two plots?
Yeah. So this is the qubit state after when I do the parity measurements. This is the reconstructed probability of there being a photon or not based on these measurements. Yeah. And of course, I mean, these add up to 1. Either there's no photons or there's 1 photon. But it's sometimes nice to plot.
That's sorry, on the left. What is the blue and the red?
So again, when I measure the qubit, I actually what I'm doing is I'm measuring the voltage coming out of the readout signal, and from that voltage, I need to make a decision. Is it in the ground state or is it in the excited state? So I actually just assign a probability. So with 90-something% probability, that was a ground state measurement. And with very, couple percent probability, it was an E state measurement. So
you have 2 lines.
Yeah, so this is the probability that the qubit was in the ground state, and this is the probability that the qubit was in the excited state based on a single measurement.
So it's like two measurements.
It's just one measurement.
One and red is the other one.
They add up to 1, right?
They add up to 1.
They
add up to 1. Okay. Yes. I mean, you'll see why I plot both of them. They obviously should add up to 1, but from the next example, you'll see why I plot both of them. Right. So I do this again, but now there is a photon. Well, I think there is a photon in the cavity. I put 1 in myself. And what you see is that the qubit state with very high probability is flipping between ground and excited, ground and excited, ground and excited in each of the subsequent measurements. And so when I do the reconstruction now, I see with very high probability, that's the orange curve, that I have one photon in the cavity. And most importantly, there's a very, very low probability that this sequence occurred because of a series of errors, even though there were 0 photons, right? And the scale on the y-axis over there is logarithmic.
There is an error, right?
There was an error. An error did happen here, as you've clearly identified, but over the course of 30 measurements, 1 or 2 errors is inconsequential because basically of this. As you linearly increase the number of measurements you make, you get an exponential suppression of the false positive probability. Right? So with 30 measurements, I get 10 to the minus 14 suppression of the probability that this sequence came from there being 0 photons. It was actually a series of, qubit jump, readout error, qubit jump, readout error, qubit error, right? And so by putting all these measurements together, I can get this reconstruction here. And I get, as you can see, the straight line down, even though there's a little bump here corresponding to where I made the error. So when I make the error, I don't gain any more information. I can't reduce the false positive probability anymore, but then I keep making more measurements and I keep going down.
So there is one thing here that I'm confused now.
Yeah.
When there is one photon in the cavity, why is it to keep changing the state?
Yeah, this is a good question. Remember in the parity measurement, I kind of was intentionally said, when there are no photons in the cavity, the qubit state remains unchanged. But when there's one photon in the cavity, the qubit state flips. Not necessarily that it goes from ground to excited, but it just flips. And the reason is, if I started in the excited state first, it would flip to the ground state. If I started in the ground state, it flips to the excited state. So here what actually happens is I start in the ground state, flip to the excited, flip back to the ground, flip to the excited, flip to the... So you could instead, in between each measurement, reset the qubit if you wanted, and then it would just all look excited, this trace. But I don't actually reset the qubit. I want to go as fast as possible. So I go to ground, go to excited, ground, excited, ground, excited.
And then if there were no photons, then you would not see this.
You would see this. No change in the state of the qubit as you make more measurements. Exactly. Absolutely. And so that's the signature here. If it's flipping back and forth, there's probably a photon. You have to do the math to be sure with very high confidence that there, in fact, is a photon.
How much time does it take to make one two consecutive measurements?
It's a couple of microseconds. And so, yeah, maybe I missed saying this earlier, but the lifetime of a photon in the cavity is about 500 microseconds. And so to make, 30 measurements of the same photon, it takes maybe 100 microseconds or something, approximately. And so that is a concern here. You have to measure faster than the photon leaves, right? Of course. And so that you have to set up the timescales correctly.
These timescales change as you choose the frequency that you set up very much. I mean, I guess at some point you're going to discuss how you span across the frequencies, like in a scope or something.
Yeah.
So my question is, if you move away from this sort of fixed frequency that you're clicking right now,
Yes.
do you run into problems with photon escape or having exponentially longer parity measurement timescales?
I would say probably not. The reason is, this is a few slides back, but we can get to it. You can see sort of how things in the system are already gigahertz detuned from each other. So even if you happen to move one of the modes by, say, a few megahertz, it doesn't really change the protocol very much. Maybe instead of, let me move here. This time that I have to wait for the qubit to go around, maybe instead of being 400 nanoseconds is 410 nanoseconds or something like that.
But if you want to now approach 20 gigahertz or something like that, is more my question.
You just have to make a new device because I don't think you could even tune to 20 gigahertz from where we are at the moment. But in that case, if you're tuning so drastically and you somehow were able to, things would probably change a little bit. But I wouldn't be that concerned about it because I can always just measure this chi. I just know what it is, and I just wait the right amount of time in order to do the parity measurements. But I don't think we could tune a cavity from 8 gigahertz to 20 gigahertz.
Sorry, yeah.
I like the optimism though. I wish I could. But yeah, maybe we'll get to this at the end, but I actually think this sort of device that I've been working on, where you count the photons, should actually be a device that never gets tuned. There should be a separate device for your axion searches that you should tune.
So you build a bunch of different qubits, and then there are many different experiments that are probably many different.
You would have to do that all so that they sort of match a different range.
Yeah.
But I think actually the right way to do this is, we can get into the details, but you have one cavity that's accumulating photons from the potential dark matter, take those photons and you throw them into here.
Okay.
And we can do that via frequency conversion process, so the frequencies of this system just never have to change.
Okay.
And so you can do this identical protocol regardless of what frequency the tuned cavity is at.
Okay.
That's my ultimate goal for an axion search, but we can get into details a little bit later. Okay, so we were here. Yeah, I'll just stress again, only a linear increase of the number of measurements, but exponential suppression of your ability to reject the false positive possibility. That's a win everyone will take. Okay, so I'll walk you through this plot a little bit. The next step is sort of to calibrate our ability to measure photons. So on the horizontal axis, I have the mean photon probability that I'm injecting into the cavity. This is something I do myself with a probe tone inside of the cavity. And on the vertical axis is the measured photon probability after I do the repeated parity measurements, apply the hidden Markov model analysis, and use the statistics of many measurements to do this. And so there's sort of two parts to this plot that I think are relevant. One is up here at sort of higher injected photon probabilities, where you see this linear relationship between what you inject and what you measure. And we do that with something like a 40% efficiency. We've gotten better and better as we improve these devices. I think we can get as good as something like 85%, which is reasonably good, I think, for measuring a single photon. And the second part of this plot, I think that is most important, is sort of where this flattens out over here. So even as I reduce the number of photons I inject all the way down to not injecting anything, I measure some background of false positives here, sort of at the 10 to the -4 level. And this is kind of interesting. The thing we wanted to think about next is, well, why do we have these false positives? I just told you in the previous plot, we've exponentially reduced the false positive probability coming from errors of the qubit and the readout and stuff. But maybe one thing I'll point out quickly that'll come up a little bit later is that comparing where this false positive probability level is relative to what you would get if you were just using linear amplification with the best amplifier, again, on a log scale, is something like 15 or 16 dB, in which I'll show you the scaling of how that works for a dark matter search, but it's pretty significant. And so this is already a win. Maybe not the best we can do, but it's already much better than what we've been doing previously with typical searches like this.
Sorry, in this book, how do you determine the injected number of photons?
This is a good question. Basically by using the fact that, well, I use my cavity, my qubit, to measure the spectrum. Let me just go to the plot. I use something like this. So I vary the injected power into my cavity. I take a spectra of the qubit, and the relative heights of these peaks correspond to a Poisson distribution of photon numbers in the cavity. And I can get the mean injected photon number in the cavity based on looking at the spectrum of the qubit. Of course, I have to average a lot in order to see this, because sometimes I'm putting very small amounts of photons. You can see very small probabilities, but you can measure. I measure a bunch here usually, then I sort of extrapolate down to I just reduce the power that I'm sending into the cavity in order to do this. And let me see if I have a plot. I do something like this. These are various injected photon numbers, and these are the various spectra that I measure. And then I can sort of extrapolate from this curve, right, just by looking at the relative heights. What is the relationship between injected mean photon number and the AWG amplitude that I put into my cavity.
In order to produce this type of plots, this is just the spectroscopy of the readout cavity. You don't.
It's actually a little bit more complicated. This is spectroscopy of the qubit while measuring the spectrum of the readout cavity. It's a little convoluted, but it's the way we.
I mean, there are no these type of pulses that these pi pulses. This is different.
We do it pulsed, but it is still a spectrum. Like instead of sending a tone continuously, we pulse the tone each time at each of those frequency points. Okay, so one thing we were curious about is, well, what are these events happening here that lead to this false positive probability? And one of the things we ended up looking at was two cases, one where I inject a relatively large mean photon population, and one where I inject a very small mean photon population. And what I'm plotting here is a histogram of all the events that I measured. I've cut off the scale here at 4 because a lot of the times I measure 0 because I very rarely put a photon in. And on the horizontal axis here is the log likelihood ratio. So this is how likely exponentially is this event to be a photon. So the larger this ratio is, the more likely it is to be a photon. The closer to 0 this ratio is, the less likely it is to be a photon essentially. So when you inject a significant number of photons into the cavity, or a significant population of photons, you see a lot of events that are at these high likelihood ratios. But when you inject a small photon population, you expect there to be no photons. At least for 6,000 events that I did, 6,000 times 10 to the minus 6 is less than 1 photon that you expect, but you still count a few, right? And so these are, I believe, these are real photons that are inside of your cavity that you are correctly measuring as real photons, even though you didn't inject them. And so what we conclude is that what we're measuring now is a background of real photons inside of our cavity. And I think this is important because we've entered a new regime where we're no longer limited by errors of the measurement itself at the few percent level, but now we're limited by real photons that exist inside of the cavity at the sort of few times 10 to the minus 4 level. It's better. I think we can still do better. And I have a whole slide. This is like a whole field of work of why are there these photons, right? At the tens of millikelvin temperatures that we operate, we expect this number just from thermal occupancy to be 10 to the minus 10 or 10 to the minus 12 or something like that. But we see 10 to the minus 4, which is much worse than what we expect, but it's still better than what you would do with the typical amplification technique.
I have a question, which is if you can measure your injected photons by taking a spectrum of your qubit,
Yeah.
why are you doing this whole parity measurement?
Because that's average measurements. With the parity measurements, I can tell in this measurement there was a photon. It's single shot measurements, right? And the averaging for the to get the spectrum takes forever. It's not something you want to do.
Okay.
It's useful when you're trying to characterize your detector, but once you have a detector that's characterized, you're just done. You just go in and count in every single instance. Was there a photon? Yeah.
When you create a photon, how long do you wait to disappear?
So the simplest way is just wait 10 times its natural lifetime, just let it decay away. But we have some clever techniques where we can convert that photon into a photon in a lossier cavity, and then we can let it dissipate much quicker. So sort of at the few tens of microseconds instead of the 500 microseconds. But the simplest way is just if your photon has a natural lifetime of 500 microseconds, wait 5 milliseconds. And usually it's gone. We did do some interesting analysis where I checked sort of telegraph noise to see if I was measuring a photon in this measurement and in the next measurement, but we didn't see any correlation between the two. So I think we were waiting long enough between the two measurements. Okay, so I think this is probably the most interesting thing for a person who's thinking about dark matter. But the way you think about the dark matter search is how long do I have to integrate my signal such that I can beat down the noise that I'm measuring? And the noise either comes from your amplifier noise or it comes from a background of real photons in your photon counting experiment. doesn't really matter, but the idea is the same. You need to integrate for long enough such that your signal counts are bigger than the variance of the background counts. And what that means is there's some requirement for the time that you need to integrate. That's related to the background rate of events, whether they come from amplifiers or anomalous photons in a cavity. And so comparing the background that we get for the photon counting experiment versus what you get for quantum limited amplification, you can already see there's an orders of magnitude difference, and that corresponds to having to integrate at each particular dark matter hypothesis for a much less amount of time, by a factor of 1,000. And as a grad student who has to do these experiments, I'm going to take a factor of 1,000. That probably means I'll graduate versus not graduate. That's actually important. And so I think this is an important step in sort of combating the difficulties of a dark matter experiment, especially in their scaling as you scale up to higher masses or frequencies. Okay. So how does the actual dark matter experiment potentially work here? The way we do it is you just sit there and you wait for the dark matter to potentially bring up your cavity. And the amount of time you have to wait is pretty much the lifetime of the cavity to do this. And then you apply these parity measurements, something like 30 of them repeatedly. And then you do this again and again and again. And we did this a couple of times. So the first time we had sort of a background of a 7 × 10⁻⁴. We did very few measurements and had something like a 65% duty cycle. The duty cycle means how long is the measurement time compared to the total time, right? And you want to reduce that as much as you can so that most of the time you're integrating the signal rather than spending time measuring the signal. We made some improvements, put some filters and attenuators in our system, increased the readout of the qubit to make these measurements go a little bit faster. So we increased the duty cycle, and we had a bit of an improvement in the background as well. But maybe as an example, what we also thought of is based on these effective searches that we did, can we say something about the dark matter itself, or how would you say something about the dark matter? And of course, we didn't have a magnetic field, so we weren't doing axion searches. We were doing a hidden photon search. So based on these observations, we could put some constraints on hypotheses of hidden photons in this case. So I'll quickly show you what that looks like. So many of you may have seen a plot like this, but let me just quickly explain it. On the horizontal axis is the potential mass of the dark matter, in this case, a hidden photon dark matter candidate. I've converted it into photon frequency on the top. And on the vertical axis is the epsilon parameter here that tells you how likely it is for a hidden photon to convert into a microwave photon. And each point on this plot is a potential dark matter hypothesis. And the way we think about this is, how much of this can we rule out, or maybe can we discover the dark matter? This experiment, we didn't discover dark matter, but we were able to rule out some portion of this plot, so rule out certain hypotheses. And it corresponds to something like this, this little javelin-looking thing. And if you zoom in, it has this really interesting structure. But the most important thing is right here at the mass corresponding to the frequency of the cavity, you get the best exclusion of potential dark matter candidates. And of course, people who are interested in the details of why this shape looks like this, I'm happy to chat a little. Key is, of course, you get the best exclusion at the cavity frequency, which makes sense. That's where you're most sensitive to photons. Okay, so kind of want to move on and talk to a second thing that we've been working on here. So most of the time here, I've been focused on our ability to beat down the backgrounds of our experiment. I haven't said anything about the signal at the moment. I just assumed if there's a signal, it's going to be at some level. If we reduce the background, we just get better signal to noise. The other side of this equation is, of course, can we enhance the signal potentially, while also, of course, using the same background reduction, noise reduction techniques that we've been talking about with the photon. And this idea comes from very simple quantum mechanics. And the idea being stimulated emission, where what we think about is you initialize the cavity in a state here with exactly n photons. the dark matter looks like a displacement of the cavity. And what you want to look for is, do you see n+1 photons? Of course, with n equals 0, this comes back to the case that we've been talking about before. Start the cavity with nothing and look for 1 photon in the cavity from the dark matter. And so if you go through the math, you see that the signal that you get is not just the mean photon number that you get from the dark matter, but you get this enhancement by n+1. And I went through the math here. It's a few lines of algebra, and I'm happy to go through it and sit down with people. But basically, you're acting this A operator on this, and you get a square root of n+1 that comes out. This was just this quantum mechanics. I had to go on Wikipedia and check that this actually made sense because I had forgotten from graduate quantum mechanics. And so this idea is, can we actually start the cavity in exactly this n state and see this enhancement into the n+1 state? For a typical linear system, this is actually not as simple as it sounds. It's not very obvious how to do this. For linear classical systems, when you drive something into the cavity, you actually don't create exactly n photons. You create a coherent state of photons. So superposition of 1, 2, 3, 4, 5, 6, so on photons. And so it actually is a little difficult to make these states. But with a qubit in there, it becomes relatively simple to make these interesting states where there are exactly 3 photons in the cavity. And there's many ways you can go about doing this. The way that we've been thinking about it is using these optimal control pulses to allow you to create these non-classical states where the distribution of photons is not Poisson, right? So it's not a coherent state. It's this interesting exactly n equals something photon number. We call these Fock states. So apologies if I use that terminology later, but forgot to mention it. So using basically just a really fast computer and inputting all the parameters of a Hamiltonian, there's quite a few more that I haven't included here just for simplicity. It'll spit out, how should I drive my qubit? How should I drive my cavity? Such that I end up in exactly 3 photon state. You can see what the simulation is as I track this evolution over time while I play this pulse. And you can see the measurement here as I track the population of the cavity, ends up right here with, I think, 3 photons exactly. And we can maybe go back and look at this more carefully. So here's some experiments where we use these optimal control pulses. Well, to create 0 photons, there's the easiest optimal control pulse. I just did nothing. But to make 1, 2, 3, and 4, we have these different optimal control pulses. And on this plot, I'm again showing the spectrum of the qubit, whose frequency is now shifted based on the number of photons in the cavity. So you can see here with 3 photons, I only see a peak here 3 shifts away. I don't see any peaks here at the 1 or 2 or 4. And so we are using these optimal control pulses to make these states. We can measure the spectra of the qubit. Another thing we wanted to measure is look at the phase space distribution of the cavity state. And that's the data over here on the right. So these are called Wigner tomograms. The idea being, if you see a perfectly azimuthally symmetric state, you know you've created a Fock state, right? And the reason for this is exactly the thing I was describing before. If you know your amplitude or your number of photons very well, you don't know your phase at all. And that's exactly what you see. This state is distributed across phase equally. And so this is, I think, an ideal state for sensing the dark matter because all you're looking for is a shift in the state. But you don't know which direction the dark matter is going to shift you, so you might as well create an azimuthally symmetric state in the phase space. It just means create a number state. Okay, so we did this. We created the states. Then the goal is to look if the dark matter came in, push the state, and then we look for the state at n+1. And I won't rehash the things we already talked about, but rather than using an interferometric measurement to measure between even or odd numbers of photons, we can ask questions like, are there exactly 2 photons in the cavity, or are there exactly n+1 photons in the cavity? I'll spare you the details of exactly how we do that, but we just send a pulse at the exact right frequency to do that. And then we, of course, apply our repeated measurements to mitigate qubit and readout errors, apply the hidden Markov model analysis, and we can put this all together, and we end up seeing something like this, where, again, on the horizontal axis is the injected photon number while I've prepared 0, 1, 2, 3, or 4 photons in the cavity, and then I measure the occurrences of n+1. And so you can see as I increase the initial Fock number that I create, I see more and more occurrences at n+1. And this is exactly scaling with the n+1 enhancement that I'm seeing. There's a little bit of inefficiency here, mostly because we don't create the states perfectly, but also the states decay while we're making the measurement. So we don't exactly get n+1. I think we get something like 60-something% of n+1. With that, maybe I'll conclude this section of the talk. We recently put this work up on the archive, so I'm happy for people to check out the supplement. There's a lot of good stuff in there, and I'm happy to answer questions about that as well. And I think maybe I'll conclude with talking about what some of the next steps in these experiments are. Jordy asked me about this earlier, but one of the things I'm really interested in is we measured the state of the photon many, many times repeatedly in time, but something we could do is take many qubits and measure the same photon in space. And this is one of the devices that I've built to do that, where you can have 4 qubits coupled to the same cavity and measuring the same photon potential. And then I think the biggest thing that is for this field to do next is figuring out why there are backgrounds of photons in the cavities, and then figuring out ways to mitigate those things. So I won't bore you with the list of things, but there's a few ideas, including cosmogenic radiation, cosmic rays, just high frequency photons. And there's lots of ideas for ways we can potentially mitigate this. So I mentioned that our background was something like a few times 10 to the -4. I think that relatively simply, just by making a few adjustments to the way we build our setups, we can get down to 10 to the -5 backgrounds, and doing better than that, I think, is going to require some serious material science and engineering to do that, to do those things. And as you can see, this is a big field of study, and this is very relevant to people in the quantum information world as well these days. And of course, the lower you make the background, the more impactful your photon counting becomes, right? Because that's the limiting factor. Okay, a couple other things I want to mention is we talked a little bit about tuning. I personally think mechanically tuning a cavity is a very difficult challenge. So one of the things we've been playing around with is potentially electronically tuning one of these cavities. Of course, this is a very difficult experiment to do inside of the magnetic field. So we're just doing this for hidden photon surges at the moment. But we pretty much take one of these qubit type devices, put it nearly in resonance with the storage cavity that we're working with, and just move its resonance about to change the coupling and change the shift of the storage cavity. And we can move it something about 10% of its frequency. So set, 8 gigahertz, we can move it something like 100 megahertz, so around 8 gigahertz, which is nothing to sneeze at, right? Okay. And the last thing is just a picture at the moment, but how I envision what an axion search would look like. So going from the hidden photons to the axions, I think I drew this diagram earlier on the whiteboard for some people. But the axion search involves magnetic field, which does not play well with the superconductivity of both the qubits as well as the cavities I think about using. And so I think the future goal should be something like separating the detection of a photon using this type of storage cavity and qubit, and the accumulation of the photon from the dark matter, and finding a way to couple these things. I think this is a project on its own, this is a project on its own, and this is also a project on its own. So I think they're all very complicated things, but people have worked on all of these things separately. And the next goal is to try to put them all together. And so with that, I think I'll conclude. I've probably gone over the hour at the moment. And I'll leave you with some references for. So thank you very much for being here, and thank you for having me.
Okay, yes, thank you very much, Akash. We have time for questions now.
I don't know if you can hear the people on Zoom.
Maybe I can check if there's questions in the chat.
I see one question here. The dispersive Hamiltonian is not exact, only correct up to order G over delta squared. have you accounted for the error induced by not being perfectly QAD? This is a great question. When I wrote down the Hamiltonians of the qubit in the cavity, I probably, as some of you know, I've hidden some of the complications of it, wrote it in a very simple form, but there are actually many more terms involved in the Hamiltonian, and we do take these into account. And in addition to that, to answer the question on the chat, they were asking about how quantum non-demolition each of these measurements is. And that relates to the fact that your qubit and cavity are actually coupled to each other, and that's how you do these measurements. But sometimes the projection can lead to an absorption as well. And that happens rarely, but it does happen. And that's actually something we just experimentally measure. How often does that happen? And we take that account in our hidden Markov rule as well.
How often does it happen?
It's sort of 0.1% or something like that. So it's subdominance to the errors coming from qubit decays or readout errors, but it happens very rarely. But it does happen. And that's something we had to be extremely careful about when we started doing these stimulated emission experiments, because as we go to higher and higher photon numbers, this non-demolition probability goes up. And so we had to take that into account. Yeah, maybe a hand here? No, okay.
Okay, more questions? Oh,
Yeah.
yes,
Yeah.
there you go.
This stimulated emission, at the end, what it does is to increase the probability of, once I have a photon in the cavity, as produced by dark matter, is more effectively detected.
I would actually say it's, if there is a small push from the dark matter, it's more likely to result in a photon at n+1. You still have to go and detect it afterwards. This is on the signal side, I would say.
You really modify the action to photon probability conversion.
Yes. Right. For the same reason that if you start a swing from standstill and you push it, it moves some amount. But if the swing's already moving and you push it the same amount, it'll be more impactful. It's a similar concept. Yeah.
I'm actually confused about a similar thing, but there's a back reaction process of the photons simulating axions and leaving, and that should be proportional to exactly that same factor.
Yes, I agree.
So they should cancel in some sense. Normally, like what you would do, I think, is you write down the Boltzmann equation, you get the statistical factors of the one product plus the occupation plus one minus the reverse, and the cross terms would cancel. And that's why I don't understand why this process is canceled for the axion.
I guess in that case, why would it not cancel for the vacuum case as well?
The vacuum case is always a +1 factor, there's a statistical factor. So the limit you take back down to 0, you always have a +1 factor. In other words, you would only ever equilibriate when your axion occupation will match photon occupation number. But if you have an imbalance, that +1 factor never cancels.
Okay.
The factors always cancel.
I actually not sure I understand exactly, but there is an additional thing that we sort of ignore here, which is that stimulated emission sort of works both ways. If you start at n, you stimulate to n+1, but you also stimulate to n-1, which is the same thing as converting a photon into an axion.
And they should cancel, I think.
But we're just looking at the n+1 events. They happen less often, or they happen at equal rates. They don't happen at the same time, though.
Okay, so the large n limit, you would essentially have a full cancellation and your mean predicted value would be the same.
Mean predicted, if you average them, but in a single shot, you either measure n+1 or you measure n-1.
Okay, super cool. I see. That's really nice.
Yeah. In any given shot, you either stimulated an axion into an additional photon, or you sent a photon into an axion.
So does this mean that there's sort of a limit to the extent to which you can push these characteristic initial states to large n, because then you become sort of flooded by small statistical fluctuations by
The nice thing about the Fock states is there are no statistical fluctuations. They are exact number states. Their variance is 0.
But in the limit that you started with a Fock state of, say, I don't know, 10 to 4.
Yeah.
Then you're not. Then it could be that you are stimulating, emitting an axion at the same rate as you're stimulating the production of the photon. This becomes more probable in the large n limit, and so I would think that the variance character is. Maybe that's.
I think what actually happens is you basically get a 50% hit in your efficiency.
Yeah.
Right. Half the time you lose a photon and half the time you get an additional photon. But I'm willing to take that factor of 2 over versus the factor of n that I'm getting.
Sure.
Right.
Super nice. Okay.
Yeah. So of course, the n that you should start with should be bigger than 1.
Yeah.
Right? 1, 0 and 1 is break even.
Yeah.
Right. But as you start to do 2 and 3, you just win more.
Could you recruit this factor too if you also measured the destruction process?
Yeah, you can measure the other side. The reason we don't is because we get confused between a stimulated emission into an axion versus just a decay of the photon from n to n-1. So we avoid looking at that because we don't want to get confused between those two products. Again, for the same reason, I don't want to claim that I saw a photon become an axion when in fact it was just a photon decay event. But the likelihood that there's an extra photon coming from somewhere is much lower than a photon was lost. Right, so I only look at the upper half of this. Yeah.
So you mentioned that you're putting different qubits in a cavity, but the qubit has to stay in the right place, so you have the highest level.
Yeah, that's true. That's true.
If you put further away, you lose the sensitivity.
That's true. So what you're asking about is the electric field of this cavity, the one I'm trying to couple to, is maximal, right here in the middle.
Correct.
And so if I put a qubit down here, say it has less coupling to the cavity than if I put it up here, which is true. I just make up for it by making the dipole of the qubit bigger. Right. And so remember, the coupling between the qubit and the cavity is d dot e. The electric field amplitude is down. I can just account for with the dipole. So I build that into the simulation and the design.
And then the second one, on the detection of axions, you put some magnetic field. What is this? How much magnetic field you need?
As much as you can get. Serious answer. I mean, the signal power that you get out goes as the square of the magnetic field.
So then you can put the magnetic material, but inside you have hundreds of Tesla.
That's a good question. I don't know the answer. Yeah, maybe. Never thought about that.
Question is how you put the cavity in the signal. Well, we'll talk about it.
Yes, so we can put later.
Yeah. That'd be fantastic. Yeah. So of course, there's a lot of balance of things. I mean, maybe you can get hundreds of Tesla, but you still want this to be a cavity. You don't want it to have a quality factor of 1. Want to have some ability to ring up. I think, yeah, I wouldn't be concerned about this side of the equation for that. Well, maybe I would. People are good at shielding these types of devices from, say, 10 Tesla, but I don't know if anyone's worked with 100 Tesla on this side.
But this 100 Tesla is inside the material, you don't have outside.
Well, how is it shielded from the outside? I mean, if this is just made of copper, the magnetic field just goes everywhere.
No, it's like exchanging direction between the spins inside of the atoms.
I see. I see.
These spins, that's why they are aligned. It's exchanging direction with the field. Like in energy, it's a magnetic field, they feel 100 Tesla, but they stay there, they don't measure.
Okay.
And then there are experiments. Let's say you put a sphere of magnetic material,
Yeah.
and people measure the qubit. The experiments from Nakamura,
Yes.
they measure single magnum
Yes.
population and so on.
Right. Yeah.
You can put it in a cavity.
Yeah.
It's a magnum, it's a cavity, and it's
I yeah. Interesting. Yeah. I know for the axion experiments, you actually want to. Maybe I just don't know what the magnetic field profile of one of these magnons or one of these Higgs looks like. But for the axion, you actually want a magnetic field whose field profile is nearly matched to the field of the mode of the electric field of the cavity over the large volume of the cavity. So maybe you can fill it with a bunch of Higgs or a bunch of magnons or something. Maybe I'm not sure. Very interesting.
Well, so I think we'll leave it here since we're going to check it, but there's going to be more time if you want to talk to Akash. And so let's thank him again for this.